All right, so we are looking at logarithmic functions. All right, logs get a bad rap. I think a lot of people are not crazy about them, but we're going to learn some ways today to make it faster and easier to work with them. All right, so to begin with, when we're talking about a logarithm, we've got y is equal to the log base a of x. And notice that there are some restrictions here. X has got to be greater than 0. You cannot take the log of 0. You cannot take the log of a negative number. Also, notice that your base a has got to be greater than 0 and not equal to 1. Now, that should sound familiar because that was the same thing that was true in our last lesson with the exponentials, right? And the reason for that is that exponentials and logarithmics are inverses of each other. And we're going to see a lot of that today. So if you're not a fan of logs, here's all you need to do. Take your logarithm and switch it to an exponential. All right. So if I take my log and switch it to an exponential, I'm going to take the base of a, and it's going to become the base of the exponential. I'm going to raise it to the answer, so my answer becomes my exponent. And then it's going to be equal to what I was taking the log of. Now, that little formula, I like it better with numbers in it. Makes a whole lot more sense to me. So I would write it instead as the log base 2 of 8 is equal to 3. I would say, okay, my base of my log is 2, and that's going to be the same as the base of my exponential. And then my y value is 3, so that's going to become my exponent. And then what I was taking the log of was 8. That's what it's going to be equal to. Now, as many years as I have taught math and done logarithms, if I'm making a key like for your quiz or your test or something like that, I still put that little pattern on the top of my paper so that I have something to follow. Okay, so I would encourage you for tests and quizzes to just put, whether you like the one with the numbers or you like the one with the variables, just put that on the top of your paper just to get you started. Okay? All right, so look at the first example. We want to change the log base 3 of 81 is equal to 4. We want to change that into its exponential form. All right, so follow that same pattern that we did just a second ago and go ahead and switch that into its exponential form. All right, what you got? What's your base? 3. What's your exponent? 4. So 3 to the 4th is equal to 81, right? Okay. Now we also can go the opposite way. So again, they could ask us to switch from our exponential back to our logarithmic. So if we do that, I'm going to come over here and I'm going to say, okay, a is equal to 4. And then x, you can see right here, is 16. And then y is equal to 2. Now, more often, we're switching from logarithmic form to exponential. All right, so we're going to practice a lot more of that. So look at this next one. We have the log base 2 of 32, and they want us to simplify that. So I'm going to go ahead and put an x over here just so that, you know, that's my unknown. That's what I'm trying to find. So go ahead and switch that into your exponential form. So switch that one into your exponential form. All right, and you should have 2 to the x is equal to 32, yes? All right, now you may off the top of your head automatically know what that answer is, okay? But let's use one that is pretty easy to figure out to kind of get get some steps that we could use for some of these ones later on that aren't going to be quite as obvious or quite as easy to figure out, okay? So anytime you are looking for an unknown and it's in your exponent, what you want to do is you want to try and set your bases the same so that you can set your exponents equal to each other. All right. So I want to try and get 2 and 32 to have the same base. So I'm going to rewrite 32 with a base of 2. All right, so 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. That's 2 to the 5th, right? So I'm going to rewrite 32 as 2 to the 5th. Now my bases are the same. 2 equals 2. So I can set my exponents equal to each other, so I can say x is equal to 5. So again, that might have been one that from the very beginning you knew what the answer was. Same thing for the next one. You might be able to just look at the next one and automatically know what the answer is. But let's use that method again just to get comfortable with it, so that then when we get some examples in a minute that we can't just look at and know what they are, then we'll know what to do with those. Okay, so first off, we switch this to its exponential form. So its exponential form is 3 to the x is equal to 27. All right, how can I rewrite 27 with a base of 3? 3 to the third, right. So I could say 27 is 3 to the third. Now my bases are the same, so I can set my exponents equal to each other, and so x will be equal to 3. All right, look at the next one. So for this next one, again, I'm going to start by switching it to its exponential form. And this may be the first one that I just don't really know what it is immediately to start with. I'm looking at it going, okay, well, 4 to the 0 is 1, and 4 to the 1 is 4. Like, I'm already past 2. All right, so let's use that same method that we were just using. Get your bases the same. So how could I rewrite 4 with a base of 2? 2 squared, right. So let's rewrite 4 as 2 squared. Then what do you do when you have a power raised to a power? Multiply. So we would have 2 to the 2x is equal to 2. And of course, there's an understood exponent of 1 there. So now my bases are the same. I can set my exponent, 2x and 1, equal to each other. So if 2x is equal to 1, what's x going to be? 1/2. And when I see it, it makes sense. It's like, oh, okay, I get it. 4 to the 1/2. Remember, 4 to the 1/2 means the square root of 4. So yeah, the square root of 4 is 2. But that one might not have been as easy to see. All right, here's another one that we might want to use that method on. So start off by switching it to its exponential form. All right. How can I rewrite, forget that it's in the denominator for a second. Just think of 100. How can I rewrite 100 with a base of 10? 10 squared. So I'm going to rewrite 100 as 10 squared. Now, how do I get it out of the denominator back up to the numerator? What makes it move across the division bar? Negative exponent. Yes, so let's use a negative 2. So I'm going to move that across the division bar by using a negative exponent. So now my bases are the same. I can set my exponents equal to each other. So I can say x is equal to a negative 2. Now for the next one, there's no way to use the method that we have been using to get that answer. All right, look at the next one. If I switch it to its exponential form, we're going to have 3 to the x is equal to 1. There's no way to get 3 and 1 to have a common base. I can't rewrite them with a common base and set the exponents equal to each other. The only way that I can do this one is just by a knowledge of algebra. If you take any number and raise it to what exponent, do you get 1? 0. Yes, any number raised to the 0 is going to be 1, except for 0, but if you'll notice, that's not in our domain. So we're not going to have to worry about getting 0 to the 0. So that means that any other time they ask me to find the log of 1, that answer is always going to be 0. It does not matter what my base is. And you actually just discovered the first property of logarithms. The first property of logarithms says if you take the log of 1, it does not matter what your base is. That answer is always going to be 0. So it could be base 2, base 3, base 10, base 275. If you take the log of 1, that answer is 0. All right, look at the next one. So for the next one, we switch it to its exponential form. So that would be 2 to the x is equal to 2. What's the exponent on the 2? 1. So what is x? 1. And you just discovered the second property of logarithms, that if you're taking the log of something and what you're taking the log of is the same as your base of your logarithm, they're going to undo each other and cancel each other out and just give you 1. So if what you're taking the log of has the same base as your logarithm, then they're going to undo each other and just give you 1. And you can see why that's true when we switch it to its exponential form. All right, since we said that exponentials and logarithmics are inverses of each other, remember that inverses undo each other. They cancel each other out. They take you back to what you started with. So you'll notice that if I take the log of an exponential and their base is the same, they literally undo each other and just take me back to what I started with, to x. If I take an exponential and I raise it to a logarithm and their bases are the same, then they undo each other and they leave me with just x. All right, and then the last one says that if you have the log base a of x is equal to the log base a of y, then x has got to be equal to y. All right, think about it. If log base a equals log base a, and they've told you these two are equal, then doesn't x have to equal y? All right, so if we come over here and we say the log base 2 of x is equal to the log base 2 of 3, log base 2 equals log base 2, so what does x have to equal? What's x? 3. So log base 2 equals log base 2, and so x is equal to 3. All right. Mathematicians are always looking for the fastest, easiest, most concise way of doing something. You know, if you think about on a square root, we don't write the 2 on a square root, right? We just assume if there's no number there that it's got to be a 2 because that's the most common one that we use. So we do the same thing with a logarithm. The common logarithm, the one that's used most often, is called a log base 10. And its name literally is common logarithm. So if you see a log that does not have a base, assume that it is a base of 10. All right? So sometimes you'll see them write it like this. That is the log base 10 of 3. They can still write the base down there, but they don't have to. If there's no base written, then it is a base of 10. All right, so grab your graphing calculator, if you would, please. And let's throw these into our calculator. All right, so your log button on your calculator again, when I touch it, remember it lights up in red. So your log button on your calculator is right here. All right, so we wanted to do the log of, I can't see it, there it is, log of 3. And we also wanted to do the 2 times the log base 10 of 2.5. 2 log base 10, 2.5. Now, please make sure that your calculator is in real mode. All right, so go to mode and make sure that it's in real mode right here, because at one point we had switched your calculator to A plus BI mode, to imaginary mode. So hit your mode button. So again, you can see it right there in red. Hit your mode button and make sure that you are in real mode instead of A plus BI mode. If you're not, switch back over to that because you may still be there from before. All right, so now I want you to do the log of -1. What happens? An error message. Why? You can't take the log of a negative number. And so it's going to tell you this is not a real answer. You can't do this. All right. What if you tried to take the log of 0? Can you do that? Can you do the log of 0? No. Remember we said you have to take the log of a number greater than 0. So if you happen to forget that, your calculator can help you out there. Okay? All right, so we did the log of 3 and got 0.477. And we did 2 times the log of 2.5 and we got 0.796. All right, so any questions about how to do that on your calculator? All right, so let's talk about some graphing then. All right, so first off, we already know how to graph the exponential function. Okay, so we want to focus on graphing a logarithmic. You can graph anything on the face of the earth if you just plot enough points. All right, so let's start with, if I want to graph y is equal to the log base 2 of x, I'm going to switch that from its logarithmic form to its exponential form. So that would be 2 to the y is equal to x. Now, the exponential counterpart to that would be y equals 2 to the x. What do you notice about y equals 2 to the x compared to x equals 2 to the y? What switched? Yes, x and y switched. And remember when we learned about inverses? When you're creating the inverse equation, the very first thing is do what? Switch x and y, right? Okay, so we can clearly see that these logarithms and exponentials really are inverses of each other. Okay, so if you'll notice, it's going to be a whole lot easier to plug in y values to this equation than x, right? Okay, so let's plug in some y values. Let's put in 0. What's 2 to the 0? 1. What's 2 to the 1? 2. 2 to the negative 1. Now remember, that means when you have a negative exponent, that means move it across the division bar. So 2 to the negative 1 would be 1 over 2 to the positive 1, or 1/2. All right, how about 2 to the 2? 4. And 2 to the negative 2 would be 1 over 2 squared, or 1/4. All right, so go ahead and plot those points that we just got there, if you would, please. And then once you plot them, play dot to dot, and that will give you your logarithmic function. And you should get something that looks like this. All right, so let's review for just a minute how to graph our exponential functions like we learned in the last lesson, okay? We had 2 landmarks. If you remember, we had an intercept at 0, 1, and we had an asymptote at y is equal to 0. So I've got the intercept at 1, I've got the asymptote at 0, so I know what this piece of the graph looks like. And then all we needed to do is just come over here and plot like 1 point to know how steep to make it. So we plug in 1, 2 to the 1 is equal to 2. So that was how we graphed our exponential in the previous lesson, okay? If you remember, when you graph an original function and you graph its inverse, they reflect in something. What do they reflect in? The line y equals x, all right? The line y equals x is this diagonal line right here. And y'all, we just graphed that logarithmic by hand, and we just graphed that exponential by hand. But you'll notice that if I folded this on that dotted line, they would fold right on top of each other. So we have seen algebraically that they're inverses, and now we've seen graphically that they're inverses as well. All right, so since we are already comfortable with the exponential function, it can really help us out with the logarithmic, because look at this. Remember that x and y switch places in an inverse, right? Okay, so look, the intercept was 0, 1 on the exponential. It's 1, 0 on the logarithmic. The asymptote was y equals 0 on the exponential. X and y switch places, so it's x equals 0 on the logarithmic. The domain here is the range here, and the range here is the domain here. So now we have 2 landmarks for a logarithmic. It's an x-intercept at 1 and a vertical asymptote at 0, okay? So our 2 landmarks for the exponential that we learned in the previous lesson were a y-intercept at 1 and a horizontal asymptote at 0. If you'll notice, the logarithmic has an x-intercept at 1 and a vertical asymptote at 0. So if I want to come over here and I want to graph the common function, log base 10 of x, I'm going to start off with those 2 landmarks. I've got a vertical asymptote at 0, and I've got an x-intercept at 1. And I know what the basic shape of the logarithmic looks like. It's going to look like this every single time. So this piece down here is going to do the same thing every single time. It's going to start at that y-intercept, and it's going to approach that asymptote. So I know what half the graph looks like anyway. Now I just need to figure out this other piece up here. Like, I don't know how steep to make it. I don't know if it's coming up here, or if it's going down here, or if it's going kind of somewhere in between. So I need 1 point over here. And again, if I've got y is equal to the log base 10 of x in its exponential form, that would be x is equal to 10 to the y. It's going to be a whole lot easier to put in a number for y. So I'm going to put 1 in for y. So when I put 1 in for y, what am I going to get for x? 10. So I would have the point 10, 1. So way out here, come all the way out here to 10 and go up to 1. That thing's going to be really flat. So that is the graph of my common logarithm. Y is equal to the log of x, the common logarithm that has the base of 10. Okay, so you know what's next? After they know that we can graph the original function, then they start asking us to shift it and reflect it and stretch it and shrink it and all that other stuff, right? Okay, so here's our basic function, the log base 10 of x. So now what's this minus 1 going to cause right here in the blue equation? Okay, so horizontal shift, right? Because it's stuck to the x. It can't be moved to the other side and grouped with the y. So what's being subtracted from x is a horizontal shift. So that's going to be a horizontal shift of a positive 1. All right. So all we're going to do is we're going to take, if my asymptote was at 0 and I horizontally shift to positive 1, where's it going to be? At positive 1. If my intercept was at 1 and I horizontally shift to positive 1, where's it going to be? 2. So there's my asymptote at 1. There's my intercept at 2. And I know what my graph looks like, so I can sketch it. It just kind of ends up looking like a shadow of the other one.
Ms. Whitmore?
Yes, ma'am.
Mallory Robinette is leaving.
Okay, thank you.
Thank you.
All right, so let's look at the red one. All right, what is this 2 going to cause? Can it be moved to the other side and grouped with the y? Yes. So is it horizontal or vertical? Vertical. Yes, it is a vertical shift of what? Positive 2. All right, so we are going to go back to our green graph, and we're going to take that point, and we're just going to go up 2 and draw the exact same thing. So there's our red graph with the vertical shift. All right, now you might remember yesterday when we were talking about our exponential functions in our last lesson, we worked with something called the natural exponential function, and we used a letter to represent that. Do you remember what it was? E, yes. So if we have a natural exponential, we have a pretty good idea that we're going to have a natural logarithmic too, right? All right, so your natural logarithmic is just, instead of the log base a, it's the log base e. So the log base e of x is equal to y. And again, you can see if we switch that to its exponential form, x equals e to the y, the exponential function is y equals e to the x. There again, you can see that x and y switch in places and then being inverses of each other. Yet again, mathematicians came up with an abbreviation for this. They couldn't use the thing about, hey, just leave out the base, because we've already got that for the base of 10, right? And so for log base e, because we use it so often, they abbreviate it ln, all right? So you can think natural log ln, maybe instead of writing NL for natural log, they thought it looked more like a log if they wrote it this way. So maybe you can think of it as el log de natural. I don't know, but this ln is natural log. So when you see ln, it means the same thing as log base e. So if you have ln 2, that's the same thing as log base e of 2. So they've gone back through and rewritten those same properties for us that we had earlier in the lesson, where remember it was like the log base a of 1 is equal to 0. Now they're saying log base e. And log base e is the same thing as ln. So we could say ln 1 is equal to 0. There is also an ln button on your calculator. So again, grab your graphing calculator if you would please. All right, so your ln button, again, is illuminated in red there so that you can see where it is. So we wanted to do ln2. There it is. And then we wanted to do ln -1. Now, before you hit enter, what do you think is going to happen? Error. Because just like with the regular log, with a natural log, you cannot take the log of a negative number or of 0. Now, something that's kind of cool is if you look over here at your ln button, right above it, see how it says e to the x? That's because they're inverses of each other. If you come up here and you look at x squared, right above x squared is the square root, right? Because they're inverses of each other. So your calculator will even remind you that these are inverses of each other. All right, so we plugged in ln2 and we plugged in ln -1. All right, so now let's look at doing some of these by hand. All right, so this first one, we've got ln 1 over e. I could put that in my calculator, but we want to do this by hand. All right, ln 1 over e. To begin with, I want to get that e out of the denominator. What makes it move across the division bar again? Negative exponent, yes. All right, so that would be ln e to the -1. Now, remember we said that when two things were inverses of each other, they undid each other, they canceled each other out. All right, so if ln is log base e, then if we have ln e to the x, that's just the log base e of e to the x. You have a log of an exponential, your bases are the same, they will undo each other and just leave you with that exponent. Y'all, literally, the ln e undo each other, and my answer is -1. Oh, I would not have remembered that shortcut, and I would have gotten it wrong. No, if you didn't remember the shortcut and you did it the same way that we were doing earlier, you'd still get the right answer. It takes a little bit longer, but you still get the right answer. Look at it. All right, if you had ln e to the -1, ln is just the same thing as log base e. So what we were doing before was we were switching these to their exponential form, right? And so we would just say e to the x is equal to e to the -1. Now my bases are the same, so I can set my exponents equal to each other, and x is -1. So if you did this the way we were doing it before, you'd get the same answer, but we would very much like to take the faster, easier way, right? Okay, so look at this next one. ln e squared, what happens to the ln e? They cancel each other out, so what's your answer? 2. How about this next one? What are you going to get? What happens to the ln e? Cancels out, so your answer is 0. And then over here, we just have 2 times ln e, so we're just going to take 2 times whatever we get for this guy right here. What's your exponent on that e? 1. So ln e cancels out, and you get what? 1. And so 2 times 1 would just give us 2. All right, then the last thing that we want to talk about is domain. All right, remember we said that you cannot take the log of 0 or a negative number. Whatever you're taking the log of has got to be greater than 0, right? That is exactly how you do your domain. Whatever you're taking your log of has got to be greater than 0. Every single time, every single logarithm, you will take whatever you're taking the log of and make it greater than 0. Because you can only take the log of things greater than 0. Okay, how do we solve that? Add 2. And so we would get x is greater than 2, or if they wanted interval notation, we could give 2 infinity. That's fine as well. All right, look at the next one. So for the next one, we've got ln 3 minus x. So whatever we're taking the log of has to be what? Greater than 0. So what are we going to do with the 3 minus x? Make it greater than 0. Yes. So 3 minus x is greater than 0. All right. Then to solve that, I added x to both sides. You may have subtracted 3 from both sides. And if you did, you would have to divide by a negative. what do you do with an inequality when you divide by negative? Switch the sign. So if you do it that way, just be sure that you reverse your sign. Okay, so we get 3 is greater than x. For some reason, we always like the x on the left-hand side instead. So I'm going to turn that around, but if you turn it around, remember you got to keep the little n towards the x and the big N towards the 3, right? So little n towards the x, big N towards the 3. 3 is greater than x is the same thing as x is less than 3. And so again, there would be our interval notation for that as well.